Okay, this is the second classical problem from the first midterm of 2024-25 fall term. In this problem, so midterm 1, problem 2, this problem we have something like a Atwood machine, except it's a bit more complicated. We have two pulleys, and over these there are ropes. These ropes are connected to some M1 and some M2 and some M3. Okay? And we are given that the well, no, this is for part 2. So for part A, they're asking us to draw the free body diagram separately for each of the three masses, M1, M2, and M3. Now, on M2, we are going to have just two forces acting. There's gravity, and there's the tension that's going up. So let's call these, these two tensions. So the tension over here is going to be the same as the tension over there, because our ropes are massless and so on and so forth. Our pulleys are frictionless. So and tension over here is going to be tension over there. We might call them, FT3, because this is the one attached to mass 3, and this one will be FT2, because this is the one attached to mass 2. The tension on this one is going to be upwards. The tension on this one is also going to be upwards, and so it's an internal force. It's just going to get cancelled. Now for the free body diagram of M2, we have F2G, which is M2 times G, which is 9.8. This is a capital G. I try to this way, and then we have F2T. Okay, let's change this. F3T. Okay. Now this one is also easy. Let's do that next. This has gravity. Gravity is always there. F3G, which is going to be M3 times G, and then F3T. Okay. Now these might look like equal, but they're not necessarily equal. One could be larger, one could be smaller. We're not given any information at this point. We don't know if these guys are accelerating up or down or what's going on. So I'm just drawing some arbitrary vectors over there. Right. Now for the M1, it's a bit more complicated, but not too much. There is F1G, which is M1 times G. There is F3T, let's say, and F2T pointing upwards. And again, these are not necessarily equal to each other. I just drew it that way. Possibly, one of these masses is larger than the other, so there is no symmetry between left and right. That one of them is going to be larger, but you can draw whatever you want. Okay? I mean, you should not try to make them particular. You should not pay any particular attention to their length, because you don't know anything about the problem, but you might as well write that these are not necessarily equal to each other, something like this. This is just free body diagrams. Now, using these free body diagrams, we are going to write down for part B the Newton's equation of motion, F equals ma equations for masses M1, M2, and M3, given that M1 is larger than M2 is larger than M3, and M1 is larger than M2 plus M3. So in this case, if M1 is larger than their sum, this will just pull both of them down. Okay, so this is going to accelerate this way, this is going to accelerate up, this is going to accelerate up. Now, I'm going to erase this, though they will come handy when we're solving this part B. The free body diagrams are useful for writing Newton's second law. How to solve this? Now, there are a couple of ways to solve this, but one thing to notice is that they all have kind of the same acceleration. Now, its direction is not the same. This one is going to accelerate down, these are going to accelerate up, but the magnitude of the accelerations are all going to be the same. Okay, so the magnitude of A1 is equal to magnitude of A2 is equal to magnitude of A3, and we can just call this A. Now, there is a convention in the book, and that convention says that we take the direction of the acceleration as positive, and we write everything that way. So, on one side, when you write F equals ma, the right-hand side is automatically m times a, because a is always positive in this convention. And I'll first apply that convention, and then we are going to switch to something more formal and see that it actually gives the same answer. Now, if you're using that convention, then you're using a funny coordinate system. Okay? This is going down, so the coordinate system you have has something like this. I don't know if this is visible. I will try blue. Yeah, maybe this is better. I don't know. But this way is going to be positive, and so is this way. Now, can you do this? Yes. Right? There is no reason why you can't have these coordinates. It's one-dimensional motion, so you can imagine that you open this up and so on and so forth. But for M2, up is going to be positive. For M1, down is going to be positive. For M3, up is going to be positive. This is what I'm using. This is the convention I'm using. It is the convention used in the book, so hopefully it's familiar. But you don't have to use this one. I'm going to switch to another convention and solve the problem that way as well. So in that convention, now what would happen here? So here Ft is up and M2G is down. So F2T minus M2G is going to be M2A. Okay, the direction of the acceleration is always up. For this one, we write something very, very similar. So let's first write that one down. Sorry, F3T minus M3G is M3A. That A is this one, the magnitude of the acceleration. It's common for all of them. And then for this one, the tensions are up, but for this, down is positive. So M1G, this is positive, minus F2T minus F3T is going to be M1A. Okay? So with the convention that the direction of the acceleration is positive, or using this funny coordinate system, we can write these down. And this is actually written directly in the solution manual. Now, how would you do this? If you had a coordinate system, something conventional, like this is plus x, okay, up is plus, so these guys have negative acceleration, this one has positive acceleration, and how would you actually obtain it? Let's try it at least for one of them. So let's try for this one. Remind ourselves that this is F2G, this is M2G in magnitude, and this is F2T. Now, Newton's second law there says that the sum of all forces, the vector sum of all forces is m times A2. Okay, sum of all forces on 2, let's say, is going to be m times A2. Okay? And what are all those forces? Let's write down their x components. So this is, of course, generally 3 equations, but we're in a one-dimensional problem, so it has just one component, and we call that component x. Now, in that coordinate system, the tension is positive, so this is F2T. In that coordinate system, the acceleration m times g, but g is going to be negative, so minus m2g is going to be m times A2. Okay? Now, at this point, you don't know if A2 is positive or negative. You're going to solve your equations, and eventually you're going to find whether A2 is positive or negative from the solution of those equations. We have chosen up as positive, and if we call this the magnitude of acceleration, okay, the magnitude of that acceleration, and if we know by our reasoning that this is going down, this has to be minus M2A. Positive M2A, because up is positive. We are assuming that this is accelerating upwards, and it's going to be just positive M2A. So we got the same answer, but maybe in a more convoluted way. You can do the same thing for mass 1. Over there, again, you'll just take up as positive. The two tensions are positive this time, so F2T plus F3T, and the gravity is negative, so I'm writing just like for the other one, minus M1G, and this is going to be m times A1, but A1 is in the negative direction, so it's going to be some minus A, some minus magnitude. This magnitude is always positive, it's the magnitude of a vector, so this is going to be minus M1A. Okay? And if you take this, and if you multiply both the left-hand side and the right-hand side by minus 1, you of course get this one. Okay? And by the reasoning similar to the second one, you can get this one, and then you're going to solve them. Okay, but for this part, they're just asking you to write down the equations, so writing these down in whatever way you want is okay. Actually, writing this is okay as well. Okay? Leaving them this way would be okay with, A2 and A1, as long as you also provide this. But then taking this and substituting it there, it's not too much work. I don't know. It's a little bit shaky that you should obtain something solvable, though the question does not strictly ask for that. Okay? But you need to have, when you're writing down things in terms of quantity that are not given, you should simplify as much as possible, so you should also write down something like this if you're leaving it that way. Okay, so for part C, find the acceleration A1 of mass m1 if m1 is 40 kilograms, m2 is 20, and m3 is 12. And we are to take g to be 10 meters per second square rather than 9.8. I'm going to erase this because we will be solving these equations essentially. We will need them. And the way to solve them is that, so we have a lot of unknowns and a lot of equations, but if you actually add these side by side, I get positive F2t, positive F3t, and then negative of those. They are going to cancel. On the left-hand side, I'm going to have m1 minus m2 minus m3g. And on the right-hand side, I have m1 plus m2 plus m3a. Okay? And this is 10, and these are given to be, 40, 20, and 12. So 40 minus 20 is 20, minus 12 is 8g, is equal to 40 plus 20 is 60, plus 12 is 72. And this is 80 by 72, this becomes 9. This is 10 over 9, which is 1.1. So A is going to be 10 over 9 meters per second square, which is actually what is given in the solution manual, solution sheet. Okay, so this might look scary. There are too many unknowns and too many equations, but if you notice that you can do this side-by-side addition trick, then it works out fine. And of course, you won't be able to solve this part if in the previous part you did not have this one. If you just left everything as A1, A2, and A3, then you won't be able to solve this. So, this will be an indication that what you did in the previous part is not adequate, right? So something to keep in mind.